have like no.
Okay.
I can do that with 5.
Oh, sorry. Okay, next one. Hmm?
Well, it's time to start. Let me first ask questions. Where are your colleagues? When I see you on file.
I think in 5 minutes they're in 2 minutes.
Okay, good.
Yeah. He said that if we start at 9, then they will be forced to come at 9.
But what's wrong? Is it
No, they take bus
bus
usually-
strike or what?
No. They usually take bus at 8:40. That takes a little.
So I think now the majority is here. So let me introduce myself, and let me introduce the course, and we start our equations. So my name is Mikhail Kiselev. I'm in the Leonardo building, office number 235. Telephone extension 343. Email ICPT.I. So I will be teaching you many physics. So I'm responsible for that. And as well as you're responsible to come in time. And I'm sorry to start with a strong statement. Try to be in time, you know. If you're late 5 minutes, exceptionally it's okay. If you're late for 15 minutes, come with urgency. I will not let you come in if you're late for 15 minutes without permission of the head of diploma program and the secretary of diploma office. To make it clear. Okay? Agreed? Yes. Actually, we have a lot of things to discuss, and we are quite in condensed situation. So the lectures will be condensed enough because many body physics is a course which can require actually infinite number of lectures, especially if we are going to modern technical details. However, before I come to description of the course, a description of what we are going to learn during this 18 lectures. Let me first discuss the organization of the course. Tutorials and examples. So as I said, the lecture course will consist of 18 lectures. Most of them will be scheduled 3 lectures per week. There were some exceptions related to holidays, in particular Easter. There will be one exception, and I have to inform the secretary. Around March 18, we will need to reschedule one lecture because I'm traveling for conference. 18 2 hours lectures. 2 hours means 1.5 hour without break. This is what we have. By the way, would you like to have a break after 45 minutes, or you would like to have non-stop lecture? So then we start this week at 9 o'clock and finish at 10:30, and this is how the lectures will be organized. There will be 2 homeworks. Which will be prepared for you with problems. So I hope the first homework will be given to you next week, just as a set of problems, and I will give you, say, 1 week time or 2 weeks time to solve it, and then I will give you another homework. There will be tutorials which I have to arrange yet, and most probably they will be given by my assistant, one of my assistants. We see how many tutorials we need depending on your response, how you respond to the materials, so perhaps we will need to discuss some things deeply, and this will be done on tutorials. So I don't know yet how many of these tutorials we will plan, but definitely it should be a commensurate number. I mean, commensurate means not more than 18, not less than 2, but something like 4 or 5 tutorials would be a reasonable amount of additional classes. Yeah. Any questions? Any suggestions? Please.
Lecture notes or books.
Yeah. I will come to this. When I discuss the objectives of the course, I will give you literature, and this is good that you remind me about lecture notes. You know that all lectures are recorded, and actually this is the reason why we don't deliver lecture notes. However, I used in my previous teaching 3 previous years, at the end of the course, collect myself on lectures, burn it on a DVD, and at the end of the stay at ACTP, everybody will get a DVD with the lecture course. This is what I used to do. This is what I use every time I teach courses at ACTP. So if you like this idea, please tell me. If you say you don't need this, it will save my time. I will not do that. But I believe it's a kind of usable thing. You may take it home. You may see all recordings when necessary. Because if you know the recording from previous years are not available online, mostly, well, not mostly. One of the reasons for that is that since everything is recorded, solution of problems is also recorded, and students can solve problems just watching previous year's tutorials or lecture courses. I don't care, you know. Anytime I will give you new problems, and I will be happy if you read or listen or watch anything which help you to understand and learn theoretical physics. And we discuss it, and we discuss nice, interesting problems. So please, whatever materials you like to read or watch or learn, you are very, very welcome. Yeah. So, as I said, tutorials. So, then final example. It's not yet clear when will it take place. I arrived at ACTP yesterday night and didn't have time to discuss it with the coordinator of diploma project, but most probably it will be sometimes around April 28th, end of April. This was preliminary suggestion, so we finish our course, I believe, April 8th, something like that. So you will have 20 days for preparation, but as I said, it is not yet settled. If you have strong preference to have exam just after the lecture course, which is usually the case, I mean, the gap with the 20 days is probably too much, but I understand that you have also other courses, other exams, and everything has to be coordinated with that. But in any case, if you have any preference, any suggestion, I'm open. I try to do it for you, and I try to do it as much as it is convenient for you. Okay? Tell me. If you need to come with any questions, whatever, send me email. We arrange when it is convenient, or just knock on my door. Sometimes I'm busy, I would then say, sorry, I cannot do that. But if you send me email to discuss any question you like, if you don't understand something during the lecture, if you have any suggestion what it is better to discuss, let's do it in a way of discussion, in a way of cooperation. Don't hesitate to contact me using this information. So, last but not least, you know that in after your complete all lecture courses, you will have mini research project for 2 months, and in order to, so you will select a person to supervise you on this mini diploma project. Please collect your mind and decide as early as possible. I would probably be able to supervise maximum 2 persons. This is, well, if you see my record, usually I do that. In exceptional year it was 3 persons, but 1 was from the University of Trieste. So 1 is optimal, 2 is discussable, but I will also put some constraints and requests related to exam. So those of you who would like to make a mini research project with me, I would request you to tell me this in advance. So at least 1 or 2 weeks in advance. Early it is, better it is. And we probably have a separate discussion during the exam. It doesn't mean that this person will have a different condition on exam. Conditions on exam will be the same for everybody. But just for better understanding what are your interests and how much they fit to my scientific interest, I would like to have with these persons some little interview for that sake. Yes. And of course, exam is important as well as homework. If you don't do homework, if you get C on exam and then eventually come to me and say, I would like to choose you as a supervisor, you will put me in a tough situation. I don't want to say you no, but on the other hand, be reasonable. Please be reasonable and understand that if you show no interest to my course, if you show no interest to condensed matter, many-body physics, what's the reason to be a supervisor? Good. Any questions? Suggestions? Okay. So now we start with a discussion of the topics of the lecture course and literature. Okay. Since, as I said, many-body physics is kind of composite course which will touch upon several topics. Some of them, I believe, have already been discussed during the courses you have already had here, but some of them will be discussed in a separate course. For example, you had solid-state physics, and therefore I know that Professor Scandola taught you in great details about band structure, about phonons. So I will assume that you know these things and will not concentrate on repetition of the subject unless we come to discussion of properties of many-body systems, like thermodynamic properties, transport properties, and at that point I will come to discuss something which you already have a background for. What we are going to discuss during this course and what is not going to be discussed. So we start today with fermions and bosons and symmetry, and I believe what you will hear from me today you already know very well. But still, I would like to tell you this because it will be the basis of my next lectures. So fermions and bosons and symmetry. So this is introduction lecture, and we start today with that. Then, during this week, we proceed with the Fermi liquids. So you will learn what are the excitations in the Fermi system, and I come to the point of excitations a little bit later. What are the properties of Fermi liquids, and why do we need this concept of Fermi liquid? What kind of system this theory describes? So this will be basics theory of metals. Then we come to next chapter of many-body physics. Again, the selection of topics and chapters is a matter of taste. If you have some preference and if you feel that you need to learn something in the chapters which are not mentioned here, let me know. We may discuss it. But the next big chapter I'm going to discuss with you is actually let me say, metals, semiconductors, insulators. What are the properties of this system based on the knowledge which you get from basics of theory of matter. Then I come to discussion of magnetism, in the systems. We discuss superfluid systems. And Bose-Einstein condensation. It will help you to understand better the course of superconductivity, which will be given to you as a separate course. Then we discuss effects of disorder. Let me put here the word localization. And then we discuss many-body effects. In nanovolt, nanosystems, and strongly correlated strongly correlating systems, strongly correlated electron systems. So this is my basic plans. Of course, having said that, it's not necessarily that chronologically the scheduler will be of that sort. We might swap magnetism in theory of semiconductors and insulators, or we might put superfluidity before here. It will depend on correlation of our programs with our other lecturers. So don't take it as ultimate program corresponding also, written also in a chronological order. Any questions? Literature. In principle, you see that the course will consist in different chapters, which are, of course, closely related, closely connected. For example, there will be discussion of magnetism of metals and magnetism in insulators. There will be discussion connection between superfluidity and magnetism. There will be connection between disorder and magnetism, also disorder in metals and the way you come from metals to insulators when you add disorder to the system. Of course, effects of strong correlations will unify everything discussed here, but as far as literature is concerned, the structure will be as follows. I will give you now a few references of general use, and when we discuss each and every chapter, I will give you some additional literature which you might or might not read in order to understand better the specific subject of chapters. Okay. As far as literature, general literature is concerned, I should also say that many-body physics assumes your knowledge of quantum mechanics, basic and advanced, knowledge of statistical physics. I will not be able to teach you any of them because I have very little time, and knowledge of solid-state physics. So don't have a wrong impression that the many-body physics course will be some kind of advanced solid-state physics course. Actually, it will not. In particular, you see that in a chapter of superfluid and Bosons condensation, we will discuss quantum liquids and gases. And in most aspects, theory of Fermi liquid describing normal metal is also based on the concept of weakly interacting gas of quasi-particles or strongly interacting liquid, fermionic liquid. However, what we will be concentrating on many-body effect. It's not single particle effect discussed in quantum mechanics. It's not classical statistical physics things which are based on using Gibbs distribution. Well, of course, part of my course will be very much related to statistical physics, especially when we discuss thermodynamics. But the message is that most of books which I will recommend you are books on quantum mechanics, statistical physics, and solid state. So you just need to find the right chapter. Okay, literature. Let me put number one, the standard course of solid state physics of Ashcroft and Mermin. So it's N.W. Ashcroft. And N.D. Mermin. called statistical solid state physics. It's one of the main textbooks in the course of solid state physics in the United States. It was published many times. I will give you reference on 1976, but you can take any your favorite edition. Then I would recommend you to use Landau-Lifshitz book course. So this is LD Landau and EM Lifshitz. You know that there are 10 volumes of this course, and the volumes which will be very much related to our course are volume number 3, which is quantum mechanics, volume number 5, which is statistical physics part 1, and volume number 9, which is statistical physics part 2. Although we are dealing with many body effects, it's a very good idea to know well single particle effects, zero temperature, ground state, and so on. So please look at quantum mechanical book, and if you have difficulties with understanding of basic things, you better tell me at the very beginning, and we will go a bit slower compared to what we can do if your understanding of these things is well. And number 3, I will recommend you book of Abrikosov, Alexei Abrikosov, which is called Fundamentals of Metal Theory. So if you need, I can ask in the library to put these books on the shelf. But as I said, all the rest, all other recommendations, for example, for magnetism, superconductivity, superfluidity, disorder, and strong correlation system, will be given when we approach the chapter. Okay, questions? Good. If not, I will erase everything and we start with a discussion of today's talk. So, we start with a symmetry and statistics. Okay. The symmetry plays a very important role in our life. You know, one can see manifestation of different kinds of symmetry in our everyday life. Moreover, most of the course will be related to breaking of some symmetry, which is a phase transitions. So we will be discussing many various phase transitions, like transition to magnetic state, transition to superfluid state, and you will have a course of superconductivity where you will discuss. The whole course will be devoted to transition theory of transition to the superconducting state. Of course, the theory of phase transition will not be the central stone in the course, however, very important one. But let's start with very simple symmetry. Let's assume that we have two particles. We are talking now about quantum mechanics, and you know that in quantum mechanics, these two particles, the particles are indistinguishable. So the particles, the system of two non-interacting particles, they don't talk to each other. The state is characterized by the wave function subject to Schrödinger equation. We are talking about quantum mechanical state when two particles are involved. As I said, no interaction, and particles are indistinguishable. So the wave function is solution of Schrödinger equation, but let's do some mental experiment. Namely, let's us interchange particles 1 and 2. Psi1 and Psi2 are quantum numbers, which include coordinates, spins, or whatever other quantum numbers these particles have. So if we interchange two particles, then we arrive at the wave function Psi2, Psi1. And since particles are indistinguishable, then this wave function can be different from the previous one just by phase, nothing else. Correct? So this is a step of first interchange of two particles. Let's do it again. Let's take this state and interchange particles one more time. So again, we will have the wave function Psi1, Psi2, which is e to the power I alpha psi Psi2, Psi1, which is e to the power 2I alpha psi Psi1, Psi2. So you see, at the left-hand side and at the right-hand side, we obtain the same state. Therefore, without losing any generality, we can conclude that e to the power 2I alpha is equal to 1. This equation has solutions which can be classified in two ways. Alpha can be odd or even numbers of pi's. So alpha can be 0, pi, 2 pi, 4 pi, and so on and so forth, or alpha would be pi, 3 pi, 5 pi, and so on and so forth. Okay? Each of them is solution of this equation, and the reason why I did that is to say that if alpha belongs to first category, let's look at this equation, then your wave function Psi2, Psi1 is equal to psi Psi1, Psi2. So the wave function is symmetric with respect to interchange of the particles. However, if you look at the second class, and again refer to the first equation, so if alpha, for example, is equal to pi, or 3 pi, 5 pi, you see that the wave function is antisymmetric with respect to interchange of the particles. At this point, I should say that in principle the life is more complicated, and if you have two-dimensional system, you can have more tricky situation. associated with gradient and associated with the fractional statistics. I'm not going to touch this issue right now, but you should be aware that the arguments which I presented here are arguments of three-dimensional and higher world. We discussed what two-dimensional world gives us a little bit later, but in order to avoid any confusion and any misinterpretation of what I'm saying, I should make this remark. Okay, if we look at this wave function, which is antisymmetric with respect to interchange of two particles, clearly, if the function behaves in this way, if we put two sets of quantum numbers the same, so therefore we put psi1, psi2, then on the left-hand side we will have a psi1, psi1 is equal to minus psi1, psi1, which means that the only possibility to fulfill this equation is to have psi equal to 0. Therefore, psi1, psi1 is equal to 0. Okay, let's now give the names for object which we have just introduced. When we are speaking about system of non-interacting particles, the wave function of each is symmetric with respect to interchange of particles, namely this one. We will refer to them as bosons. While if the wave function is antisymmetric with respect to interchange of the particles, we will refer to them as fermions. I come to the point of statistics, which I believe you know very well. As I said, this is just a repetition. So the name of bosons comes from the name of Indian physicist Bose, and corresponding statistics is called Bose-Einstein statistics, where two great names, namely the name of Bose and name of Einstein, are staying together, while the name of fermions come from great Italian physicist Enrico Fermi, and corresponding statistics is known as Fermi-Dirac statistics, where two great names of Fermi and Paul Dirac stand together. I hope that the case of statistics is well known to you. However, I will come to brief summary of what you should remember about Fermi and Bose statistics. So let's keep in mind this nice conclusion, and let's now just construct the wave functions for fermions and bosons from the wave functions, single particle wave functions. Okay, if we start with bosons, and we have two particles, each of them is characterized by the wave function phi, then the symmetric with respect to interchange of argument function psi describing two particles can be constructed in a way phi1, phi psi1, phi psi2 plus phi psi2, phi psi1. Let me put 1, 2, 1, 2, where 1 and 2 will refer to particle 1 and particle 2. Once again, these particles are indistinguishable, and this is the main difference, actually, between quantum mechanical objects and classical mechanical objects. In classical physics, you can mark each and every particle, and they are not indistinguishable. And all these simple arguments come from the fact that the particles are indistinguishable. Okay. So far, so good. We see that we have a symmetric combination, and if we want to proceed with the construction of the wave function of many-body bosonic system, so we now come to many-body physics, what we have to do, we have to take the wave function of every particle and symmetrize them with respect to every possible coordinate interchange. Once again, I'm emphasizing that the particles are non-interacting. So to put it on a formal basis, let me write the wave function of n particles. So this is 2 particles. If we have n particles, we have to write down 1 over square root over n factorial, sum over all permutations, phi 1, psi 1, phi 2, psi 2, phi n, psi n. So you see that the wave function, as I said, is symmetric with respect to each and every possible permutation of coordinate, and this symmetry is encoded in this formula. The sequence of this, if we look, for example, in this simple example, is that arbitrary number of particles can occupy the same state. Namely, there is no bound that particle 1 and 2 cannot stay at the same state at all. And this will lead us to very interesting physics, which is known as Bose-Einstein condensation, which we'll spend some time for discussion. Okay, let's now come to fermions and do the same. Let's first construct the wave function of 2 non-interacting particles, satisfying the property that this is antisymmetric with respect to coordinate interchange. Psi 1, psi 2 is equal to 1 over square root of 2. And here, phi psi 1, phi 2, psi 2, minus phi 1, psi 2, phi 2, psi 1. You see that if you interchange the argument of this wave function, you immediately arrive at this property. So what one can see here is that the expression is determinant, right? I believe you are familiar with determinant. Phi 1, psi 1, phi 1, psi 2, phi 2, psi 1, phi 2, and we use a property of determinant that the change sign if you interchange rows and columns, and moreover, if 2 rows or 2 columns are the same, then the determinant is equal to 0. Based on this property of determinant, we can have a guess and then prove it that the wave function of n non-interacting fermions is given by determinant of n by n matrix. So then we write it this way. So psi 1, let me put the n particle wave function. So it's 1 over square root of n factorial, and here we have phi 1 psi 1, phi 1 psi 2, and so on, phi 1 psi n, phi 2 psi 1, phi 2 psi 2, phi 2 psi n, and so on and so forth, phi n psi 1, phi n psi 2, phi n psi n. So this is how the wave function of n non-interacting fermions looks like, and I'm pretty sure that you know that this determinant is called yeah. Good. We said that, and we are back to property that determinant is equal to 0 if two rows or two columns are the same. Or, if you look at this two-particle wave function, if the set of at least two quantum numbers is the same. What does it mean physically? It means that fermions cannot occupy quantum state, the same quantum state, two of them, or to say it in a different language, there exist no two fermions characterized by the same set of quantum numbers. And this is a strong statement that fermions can only be occupying the state once or not occupying state at all, and this statement is known as Pauli principles. So you see that there is a huge difference between bosonic and fermionic system, namely bosons are collective items. So they can be collected in a quantum state, and they can remain in a state where all particles have the same set of quantum numbers. So they can condense to such kind of state, and we will discuss it a bit later. However, fermions are kind of individual particles. They don't want to be condensed in a state. They don't want to come to the state with the same quantum numbers, and can be in the state where the given quantum number either empty or occupied. And all the rest, so the logics to come from here to here, from here, is just based on a symmetry and nothing else. Good. Let's keep this message that bosons can occupy the quantum state. An arbitrary number of bosons can be characterized by the same set of quantum numbers, while for fermions, the quantum numbers, the occupation number can be either 0 or 1. And let's proceed with a calculation of the distribution function. Yeah. The last remark is that you know that there is a theorem called Pauli theorem which connects statistics and spin. Spin, again, I believe you know it from quantum mechanics, is the quantum number which doesn't have any analogy in classical systems. But the Pauli theorem says that bosons can only be characterized by integer number of spins, 0, 1, 2, 3, 4, while fermions are characterized by half integer number of spins. 1 half, 3 half, 5 half. So I'm not going to go into the details of the Pauli theorem. I just refer it for you for your knowledge. The proof of this theorem will go far beyond this course, and anyway the proof is given in the relativistic theory. Okay, good. What are the examples of fermions and bosons? And what we are actually doing in this course. Last year, not last, 2 years ago, I was teaching the course of quantum mechanics, and I realized after some lectures that there is no good understanding of what we are doing. We are doing actually diagonalization of Hamiltonians. So we want to, if we have a very complicated Hamiltonian describing many-body physics, at the end of the day, we want to write this Hamiltonian in diagonal form, namely, we want to know all eigenvalues of this Hamiltonian which stand on diagonal, and we want to know all eigenfunctions of this Hamiltonian. And if we know that, we know everything about system, because we can calculate thermodynamic properties, transport properties, everything. But of course, for many body system with interaction, it's very tricky to do it. Sometimes it is possible, sometimes it's possible but difficult, sometimes it's hardly possible to do. So what we are doing, we adopting some approximations in order to fulfill this task and diagonalize the Hamiltonian. But when we are done, when our Hamiltonian has a quadratic form, then we can speak about quasi-particles in the system. So now I come to important concept of the many-body physics, is the concept of quasi-particles. These are entities which will describe us the system. So namely, if I start with a strongly with the interacting something, at the end of the day, I would like to come to non-interacting something, and this or weakly interacting something, and these entities will be quasi-particles of my system. So, and when I speak about statistics, I will be mostly referring to quasi-particles. So what kind of quasi-particles we have, and what are the examples of quasi-particles with different statistics? Bosons. So here, the zoo is very rich. You already heard about phonons. The quasi-particles associated with lattice vibration and motion of ions or atoms in a crystalline lattice. We will be discussing magnons, the quasi-particles in a magnets or excitations. So quasi-particles and excitations are synonymous. You probably heard about plasmons. The excitations in plasma, namely in the system of charged particles interacting through Coulomb interaction. I may add excitons here. The bound state of two differently charged particles, similarly to hydrogen atoms. Now let's give examples of fermions. And this is what we are going to discuss during next lecture. Actually, we will be speaking about electrons and holes. And if you heard about Fermi gas, you probably heard about Fermi sphere, Fermi surface, and we repeat this today. And then we come to definition of what it is. You may see that there is in fact a disbalance, that most of collective excitations are subject to Bose statistics. This is true. However, there is a big family of excitations which are characterized by Fermi statistics, and we discuss both families during the course. Good. So let's now see very quickly what is the sequence of these symmetry properties when we discuss the distribution function. Any questions? So if you feel that I'm too slow, let me know. since these concepts are important and you should have clear understanding of what we are doing and why we are dealing with these objects, then I go slow. Okay, so we will be discussing thermodynamic potential characterized in the K quantum state. In practically whole course of many-body physics, I will use the set of units where Planck constant is equal to 1, speed velocity is equal to 1, and also Boltzmann constant is equal to 1. So therefore, I will measure energy in kelvins. However, for some particular cases, we will put back all fundamental constants and also see what's the dimension of given variable. So at this moment, as I said, I will set the Boltzmann constant equal to 1, measure thermodynamic potentials or energies in terms of temperature, and by the definition, this is temperature times log zk, where zk is a partition function. So this is partition function. And this is temperature. And K characterizes as quantum state, quantum number. In particular, it could be momentum, so then you will be seeing that K is just momentum, but it can be momentum plus spin or whatever. So what Zk is, it's a sum over all occupation of quantum numbers. I'm writing you the grand canonical partition function, e to the power mu minus epsilon k over temperature to the power nk. Again, mu is a chemical potential. And I'm working with grand canonical. So are you familiar with these expressions from course of statistical physics? And then the total thermodynamic potential omega is a sum over all quantum numbers omega k. So this is T sum over k logarithm sum over nk e to the power mu minus epsilon k over temperature to the power nk. Okay. And epsilon k is so-called dispersion or spectrum of your non-interacting particles, and since particles are non-interacting, this is k squared over 2m. And here I'm saying that k is momentum. Good. So I have written general equations, but now let's implement our knowledge that for bosons nk can be arbitrary. For quantum states nk